I want you to listen and learn. Absorb it all in. Now this first chapter is on logic. What the heck is logic? It's in your notes, people. The science of reasoning. See, logic is the beginning of mathematics. See, if you cannot think logically, you cannot do mathematics. So that's why we're going to be studying logic, so you can think logically. Now the building blocks of logic are these things called statements. Okay, a statement could be something like the dog is blue, the cat is pink. But we're not going to deal with statements like that. We're going to deal with mathematical statements. So if you have a statement, normally we start with the lowercase letter q, something like this, x equals 2. That's a statement. Okay? Now what we're going to do in tonight's homework is we're going to negate a statement. What does negation mean?
Did not.
Like what if I said, okay, what if I give you the statement, the dog is blue? What would be the negation of that?
Dog is not red.
The dog is not blue. What? The dog is red. No, the dog is not. Negation means opposite. Yeah? Okay? So if this is statement P, what would be not P? See, this symbol means the negation of statement P, or we simply say not P. X is not equal to 2. It's easy to negate something like that, right? That's a simple statement. Okay? In fact, the kind of logic that we're going to study is what we call two-valued logic. That's the simplest of all the logic. In other words, every statement is either true or false. That's why it's two-valued, true or false. But if you go to college and you major in mathematics, you can study things called fuzzy logic, where every statement is a number between 0 and 1. 0 is like false, 1 is like true. But then you could also have a statement like, what is the truth value of a statement? It's either true or false. But when you do fuzzy logic, a statement could have a truth value of maybe 0.573. So if 0 is false and 1 is true, what is 0.573? It's a little more true than false. Yeah? And there's lots of applications of that. For example, like did you guys ever go to this country called Japan? Did you ride in the bullet train? You know the acceleration and the deceleration, it's really smooth. You know why? Because of fuzzy logic. Whoa. But we're not going to be studying that. We're only going to be studying two-valued logic. Every statement is either true or false. Okay, let's do some more simple ones. Statement Q is x is greater than 2. What would be the negation of that statement?
Less.
No, you could say x is not greater than 2. But to be more correct, you could say x is
less than
or equal to 2. Pretty simple, yeah? So if you have simple statements like this, it's easy to negate that. Okay, but we're going to look at more complicated statements today. Look at the ones you have for homework. So there's two kinds of statements we're going to talk about today. The first one is called a universal statement. Now let me give you an example of a universal statement. For all real numbers a and b, comma, a plus b cubed is equal to a cubed plus b cubed. Why do you think we call this a universal statement? Look at the first two words. Why do you think we call this a universal statement? Because we're talking about all. For all real numbers, a and b, a plus b quantity cubed is a cubed plus b cubed. Now, is this statement true or is it false? False. Okay, very good. It's false. Because you guys learned something in algebra too, right? In order to make this statement true, though, what would I have to change that to? Wait, let me call on somebody. Well, call me. We learned this in SAT prep.
The triangle.
A cubed
A cubed
plus 3a squared b plus 3ab squared plus b cubed.
Very good. We remembered something from algebra 2. We missed the part. Where did these numbers, what's this 1331 business? Where did that come from? Pascal's triangle. See, that's why I have to fill in the gaps that you guys have missing, yeah? You guys know what Pascal's triangle is? You start with 1 on the top, and you have 1s on the outside like this. To get the numbers in the middle, you add the 2 numbers above it. So 1 plus 1 is 2. So put 1s on the outside, 1 plus 2, 2 plus 1. Put 1s on the outside, 1 plus 3, 3 plus 3, 3 plus 1. And you can continue making this triangle for as long as you want. We call this Pascal's triangle. And why is this useful? We just showed you. Because it allows you to expand a binomial. It tells you the coefficients. Like for example, I guess we're going to start from the very beginning, yeah? What is a plus b to the 0? 1. What is a plus b to the first?
A plus B.
A plus b. What is a plus b to the second? A squared plus 2ab plus b squared. What is a plus b to the third?
That one.
Yeah, it's written there. A cubed plus 3a squared b plus 3ab squared plus b cubed. Where do these coefficients come from, Mr. Park? 1, 2, 1, 1, 1, 1. Pascal's triangle. Pascal's triangle tells you the coefficients when you expand a plus b to the nth power. So if I wanted to expand a plus b to the 4th power, what would you get? Following. So what you do is you go down to the 4th row of Pascal's triangle, and yes, that's the 4th row. Why is that the 4th row, Mr. Park? It looks like the 5th row. No, it's the 4th row. You know why? Because the first row is actually the 0th row. Why? Because it corresponds to a plus b to the 0. Doesn't it make sense? Makes perfect sense. So, following the pattern here, if you had to expand a plus b to the 5th, what would you get?
To the 4th?
So, you look at these numbers, 1a to the 4th plus 4
A to
a
the
cubed b. So look at the pattern. The powers of a are going down by 1. The powers of b are going up by 1. And the 2 powers always add up to 3. That's like the pattern, right? So over here, same thing. The powers of a go down by 1. The powers of b go up by 1. The 2 powers always add up to 4. It makes perfect sense. So what's the next term going to be? Look at the numbers. 6 a squared b squared plus 4 a b cubed. And finally, 1 b to the 4th. There you go. And you could do a plus b to the 5th, right? I'm sure. Probably save that for the quiz, yeah?
Yeah.
All right, there we go. Pascal's triangle. See, you learn something new every day. So, now, this is what we call a universal statement, and we determined it was false, right? Okay. We would have to change this to this in order to make it true. Now, in mathematics, mathematicians, we don't like to write out all these words, so we have symbols for that. So, let me symbolize this for you. This is how we symbolize that statement. So you can probably guess that this symbol here means,
upside down A.
no.
For all.
What does it mean?
Universal.
No. For all. That means this symbol means for all. A and B, what is the symbol? Is an element of the.
Real numbers.
Okay, now before we go any further, can I assume everybody knows your sets? The sets of all the numbers? Oh, okay, I think we need to do some review before we go on. Okay, let's do the review over here. Normally, we would do the review on this side of the board, but then since we're filming, we only can film one side of the board. So, let's start at the very beginning. This is the set 1, 2, 3. Like when you were in the womb, these are the first numbers that you learned, right?
No.
Yeah.
No, I'm serious. When you're in the womb, don't your parents talk to you?
Maybe.
Like they read stories and they count numbers and stuff like that?
That's possible.
You received it subconsciously. Anyway, 1, 2, 3. These are the set. This is the set of natural numbers. Capital N is the set of natural numbers. And then, when you came out of the womb, like when you were first born, then your parents taught you include 0 now, right? What is that?
Oh.
That's the set of whole numbers.
What W?
And then, then when you started to learn about there's an infinite number of numbers, right? What is this?
Integer.
The whole numbers and their opposites. These are called
Integer.
integers. And what letter do we use for the integers?
C.
Z. How do you know that? Because we learned this in summer school. But it doesn't matter because I'm teaching it to you now, right? Because some of you weren't in my summer school class. So it doesn't matter. You're learning it now. Okay, now these are the integers. Okay, now what is a rational number?
Over fraction.
A rational number.
Be written.
Okay, so the set of rational numbers. A rational number is a number that can be written as a ratio of two integers. So like, what would constitute a rational number like? Is 3 a rational number?
Yeah.
Yeah.
Yeah, because you can write it as 3 over 1, a ratio of two integers, right? What about 0.7 repeating? Is that a rational number?
Yeah.
Yeah, because you can write that as 7/9, right? What about 0.142857 repeating?
Yes.
Yes.
Yes, because you can write that as
1/7.
1/7, that's right. Someone going, what? Talking about that. Come on, didn't we learn in, when you first learned it? Pre-algebra? Any repeating decimal is a rational number. I can give you any repeating decimal and you should be able to write the fraction for it, right? Okay, let's do a test. See how I'm gonna regress on it now? 0.23 repeating. Okay, that's too hard for you. 0.2 repeating. 2 nines. Oh, like 0.7 repeating is 7 nines. Oh, you learned something today. What is 0.5 repeating? 5 nines. What is 0.3 repeating then?
1/3.
3 nines, which is 1/3. See, follows the same pattern. So what about 0.23 repeating? What do you think? 23 over 99. What about 0.237 repeating? What do you think? 237 over 99. Okay, you guys think you're good now? I think you're good. What about 0.23? Just the 3 repeats. Come on. Come on. Okay, this is how I was taught in kindergarten. Okay, watch this. 0.2333333 repeating. Okay, I don't know what fraction that is. I'm gonna call it x. What am I gonna do next? Come on, you've seen this last year. I saw your Algebra 2 book. It's in the beginning of the book. You know, when I go to the bathroom, lots of times I take the Algebra 2 book just to see what's in there, to see what you learned. What am I gonna do in the next step? I'm gonna multiply both sides by 10, and what are you gonna get? Multiply this by 10, what do you get? 2.333333, and so forth. Subtract, what do you get?
9x.
9x equals 2.1,
1.
and then everything else is all zeros, right? So therefore, x is equal to 2.1 over 9, multiply top and bottom by 10, and you get 21 over 90, divide top and bottom by 3, and you get 7 over 30. There you go. 0.23 repeating is 7 over 30. That's how you change any repeating decimal to a fraction. We don't even have to talk about the non-repeating ones, right? I hope. Maybe we do. What is 0.2 equal to? The non-repeating decimal. And don't say 2/10. What about 0.125?
1/8.
1/8. Okay, we know these.
Yeah.
Right? So any non-repeating or repeating decimal is a rational number. So that's what the rational numbers are. And what letter do we use for that? And don't say R.
The whole. I don't know.
Q. We use Q. You know why? Because what is a rational number? It's a number that can be written as a ratio of two integers,
Quotient.
which is a quotient. That's right. That's why we use Q. Anyway, R is reserved for the real numbers. Now, what are the real numbers? Okay, a rational number can be written as a ratio of two integers. What do you think the irrational numbers are?
ratio of two rational numbers.
No, it's a number that cannot be written as a ratio of two integers. Like, give me an example.
Pi.
Yeah, like pi, square root of 2, cube root of 5, right? These cannot be written as a ratio of two integers, so they're called irrational numbers. So what would happen if I put the rational numbers together with the irrational numbers?
Real.
You get the real numbers. Now, is that all the numbers that we learned? No. What is the set of all the numbers that we learned? I think I taught you this in summer school if you were in my class. The complex numbers. These are all the numbers that we know of. Now, what is a complex number again?
A plus.
Come, you gotta know this when you take the ACT and the SAT, you know? A complex number is a number that can be written in the form a plus bi. Does that sound familiar? Now, what is I again?
Imaginary.
The square root of -1. So a complex number consists of a real part and an imaginary part. So when you put the real numbers and the imaginary numbers together, we get the complex numbers. Now, I notice some of you are taking notes, but look, if you look at the notes, here. Let's look at the notes. Whoa, look at right here. These are the sets of all the numbers I just talked about. What? Whoa, Mr. Park, your notes are pretty complete. Thank you. Okay, notice that we've just been going back to remedial math, right? Pretty much the whole time. What did I actually teach you? I taught you that anytime you see for all something, comma something, that's a universal statement, and then this is how you symbolize it. We haven't even talked about negating it yet, because that's what we need. That's what you need to do in tonight's homework. State the negation of each statement. So we have to learn how to negate this statement. So can I erase all this remedial math there? Okay. How much time do we have? I thought we were going to finish it early. Guess that's not happening today, is it? Okay, here we go. So if this is statement P, how do I negate that? What is the negation of that? Well, what if somebody told you, for all real numbers A and B, this, what would it take to prove that person wrong?
Real one.
Like what if you take any two real numbers, you add them up and cube it, you will always get this over here. What would it take to prove that person wrong?
Plug-in number.
Yeah, you find just one, what do we call that? You just have to find one,
Set.
no.
Example.
I'm pretty sure in geometry you guys learned this term, counter example.
It's a mod.
Yes, exactly, Mr. Moss taught you. So, the negation of this, you know what? Just to save time, I'm just going to tell you what it is. There exists, is it there exists or there exists? There exist real numbers A and B such that A plus B quantity cubed is not equal to A cubed plus B cubed. This is how you negate a universal statement. Now, what kind of statement is this right here? There exists. What is that? There exists. That means what does there exists mean?
There are some.
Yeah, some. It means some. And what does some mean in mathematics?
False.
What does it? It means at least one. At least one. So there's at least one pair of numbers A and B such that this is not equal to that. That's how you negate a universal statement. So, what did we just learn? The negation of a universal statement is this statement. This statement here is called an existential statement. Now, if you're getting confused by this, all you gotta do is look at the form. Okay, you know what? Before we even do that, let's symbolize this. Like again, I said, mathematicians, we don't like to write out all these words, so we symbolize. So here we go. This is how you symbolize that statement. Now, in tonight's homework, sometimes I write it out in words, sometimes I symbolize it. You have to know what these symbols mean. Now, when you take the quiz or test, I don't care how you do it. You can write it out in words or you can write it in symbols. It doesn't matter to me. Okay, so you can probably guess that this symbol here means what?
There exists.
There exists. A and B are elements of the real numbers. See, real numbers A and B. And so you can probably guess that this symbol means such that. That's right. Mr. Park, that thing is like the reflection of this one. Yeah, that's right. You got to get used to that. So when you write it this way, that means it's an element of, but then when you write it that way, it means such that. Is that going to confuse you?
Yeah.
Then you're going to get confused. Such that, and then notice that this is simply the negation of what that is, right? Like if you have gorilla equal banana, what's the negation of that? Gorilla is not equal to banana. So that's how you negate a universal statement. Now, like I told you, if you're confused, just look at the form. And this is the beauty of symbolic logic. The meaning of the words doesn't matter. You just look at the form. So, for example, here, let me do this. If Q is a universal statement for all something, comma, something, for all rectangle, comma, triangle, and these represent statements, how do you negate that? Following what I just taught you here. There exists, don't say backwards E. There exists rectangle such that not triangle. It doesn't matter what words you put in there, that's how you negate it. Look, every universal statement has the same form. For all, box, comma, triangle. Right? What is the negation of that? There exists box such that not triangle. See, because if this is triangle, wouldn't that be not triangle? The negation of it? There you go. It's that simple. It really is that simple. So if you have to remember anything, that's it right there. This is it. That's how you negate a universal statement right there. It doesn't matter what the meaning of the words are. But you know what students have problems with? Everybody can negate it because you just got to follow the form. But then it says, then you have to determine whether the original statement is true or false. That's what students have problems with. So when you get to the test, see, writing the negation of each statement, that's going to be 4 points. And then determining whether the original statement is true or false, that's what, 2 points. So if you have 10 of these, you have to know which ones are true and which ones are false. So that means you got to kind of know at least some mathematics, yeah? Okay. So if the negation of a universal statement is an existential statement, what do you think the negation of an existential statement is? It's a universal statement. Okay, so let's do one. What time is it? What time does this class end? Wait, what time did this class start? 8:15? And how long are the classes? 55 minutes?
70.
Oh, 70. Oh, no problem then. Okay, so let me give you an existential statement. There exists X and A and B element of the how's that? A over B equal pi. Okay, there you go. Now what the heck does that mean? What are you thinking when you see this?
A is pi. Oh, yeah.
What? No. What kind of statement is this? Is this universal or existential? Okay, so there exist A and B are elements of the integers. So there exist integers A and B such that A over B is pi. Now, is this statement true or false?
False.
It's false because pi is not. If I can write a number as a ratio of 2 integers, then we call that a rational number. Pi is not a rational number, right? I hope you guys know that, right? Now, every year, there's always 2 or 3 people in the class. You know what they tell me? Mr. Park, my pre-algebra teacher taught me that pi is 22 over 7. No. It is approximately 22 over 7. It is not equal to 22 over 7. Why, did you guys think it was?
I didn't know that.
You know, what? Oh, okay. We got to do remedial math then. What do we know pi? Pi is 3.1415926535897. Even I forgot. 3.14159265358897. I don't know if that's even right.
No, that's right.
Is it?
Yeah.
Okay, give me more. Who knows more?
8, 9, that's all I got.
Okay, well, we just go with 10 decimal place accuracy.
It looks-
Ah, see,
it
you know
looks-
what? Let's just look at this poster right here, because this poster tells me the decimal places are 5. 3.1415926535889793. Come on, people. There's so many clues in this one. 8, 9, 7, 9, 3, and so that's 15 decimal. Look, even this poster tells you the decimal places of pi. Look, Mrs. K. Goto. You guys knew Mrs. Goto when she was here?
We weren't born.
A great pedagogue, of course, makes one grasp profound polyhedra, elusive equations, and all the calculus. You know what this is? These are the decimal places of pi. You just count the number of letters in each word. See, 3.141592653589793. Okay, so what are we talking? Oh, we're talking about pi. So, if somebody says pi is equal to 22 over 7, that's ludicrous, because what is 22 over 7?
A rational number.
3 and 1/7. And we know 1/7. Well, what is 1/7?
3.1.
1.142857 repeating. Is that the same thing as that? No. So pi is approximately 22 over 7. And that's a pretty bad approximation. I don't even know why pre-algebra teachers teach you that. If they're going to teach you an approximation, they should teach you the Chinese one. Pi is approximately 355 over, does anybody remember from geometry? Because I know Mr. Masorada teaches this. I guess not. 113. And does this sound familiar? All you have to do is remember the first 3 odd numbers. See? 1, 1, 3, 3, 5, 5. Does that sound like something Mr. Masorada would say?
Yeah.
In fact, if somebody would compute this on the calculator, who has a calculator? Do I have to do it? This is not a smart board here, people. I have to walk to my computer every time. Boo, I think I'm going to give you a strike for that.
Everyone?
Everyone?
Strike 1. Everybody gets a strike.
Yay, one
I
team.
got it.
Yeah, after I walk over here.
How close is it?
Too late, I'm doing it already.
That's
Up to 5 decimal points.
355 divided by 113. Boom! 3.141599292. So you get 6 decimal place accuracy. Isn't, look, you got 6 decimal place accuracy. Over here, you only get 2 decimal place accuracy. Which one is better? What's better, 2 or 6? You're gonna have $2 or $6?
6.
6.
But you know what better one? I'll give you one that has 30 decimal place accuracy. However, it's a little harder to remember. I hope I can remember this. Pi is approximately natural log of 640, 320 cubed plus 744 all over the square root of 163. I think that's correct. This will give you 30 decimal place accuracy. Okay, you know what? I'm gonna do it. I want to see if I remembered it correctly.
It's not that big of a calculation.
Natural log. What did I say? 640, 320 cubed raised to the third plus 744 divided by the square root. Where's square root? Oh, there. Square root of 163. Get out of the radical. Boom! Well, you can't really tell. What would tell us? Wolfram alpha?
Yeah.
Okay, let's go to Wolfram alpha. Wolfram alpha. You guys have that on your calculator? I mean, on your iPads?
Yeah.
Okay, here we go. Shh! Concentrate. What's taking so long? Do you guys have something better on your iPads? What about Desmos? Can Desmos do this? Natural log of 640, point p raised to the third power plus 744 divided by, how do we write square root?
Half to half.
163 raised to the half power, 0.5. Bam!
Whoa.
Here we go. 3.141592653589793. Well, that's all I know anyway. So we just assume you got
Trust it.
just trust me. You get 30 decimal place accuracy.
Whoa.
Just trust me. You can believe me on this one. Now, what are we talking about? What are we talking about?
Logic.
Oh yeah, okay. If this is statement Q, okay, how do you negate that? Well, if the negation of a universal statement is an existential statement, then the negation of an existential gotta be a universal statement. And again, you just follow the same form. So what do you think?
For all.
For
For all integers A and B, comma, A over B is not equal to pi. So again, just follow the form here like this. Every existential statement looks like this. There exists box such that triangle, right? So if you want to negate it, it's going to be for all box, comma,
Such
not triangle. Boom, just like that. That's how easy it is. It doesn't matter what the words are, you look at the form. You guys know what I'm saying? Okay, now, we already determined that the original statement was what? True or false? We just spent all
False.
false. This is false. So by default, remember, every statement that we're going to study is either true or false. Therefore, its negation has to be true. That's right. Pretty easy, huh? Okay, so we'll see what you're going to do with tonight's homework. Oh gosh, now I'm going to walk back to my computer.
Mr. Mark,
Is there a better way? Yeah.
you know, for fuzzy logic,
Fuzzy logic, yeah.
if you had like a statement like that, and you knew what the value on the scale of true to false was from 0 to 1, do you just,
Oh,
for
okay,
the
yeah.
opposite, do you subtract by 1?
Yeah, I don't know. I don't know how that would work. But it's not true, it's definitely false though, right?
Yeah.
It's definitely false, so I think it would be a 0, actually. Just because you have a lot of decimal place accuracy, does that make it more true?
Yeah.
You know what I mean? I don't know. That's a good question. I really don't know. Okay, the last thing you gotta know on tonight's homework is right here. We're gonna make truth tables. Now, what the heck is a truth table? A truth table basically is a table that shows you all the possible truth values for a given statement. So, let's start with the easiest one. Let's say you have a statement. Now, when you have a statement P, what are the possible things that it can be? Either true or false, right? Remember, we're only studying two-value logic. Every statement is either true or false. So, when you have the negation of P or not P, what do you think?
False.
If P is true, what would not P be?
False.
False. And if P is false, what do you think not P is? True. There you go. That's what we call a truth table. It just shows you the possibilities for each statement. Now, of course, that's the easiest one. Now we're going to kick it up a notch. Okay, what if you have P and Q? Now, let's say we have two statements. How many possibilities are there going to be in my truth table? Come on, let's use the multiplication principle that we learned in SAT Prep or in Algebra 2. How many possibilities are there going to be? If one event can occur in M ways, how many different possibilities are there for P? Two. It's either true or false. What about Q? Two, true or false. So how many possibilities are there? Four. And how did I get 4? 2 times 2, the multiplication principle, not 2 plus 2. 2 times 2. But Mr. Park, 2 times 2 is the same as 2 plus 2. Yeah, but then what happens when we get to like 3 statements, P, Q, and R? Then it's going to be 2 times 2 times 2, which is 8, not 2 plus 2 plus 2. You know what I'm talking about?
Yeah.
Okay, so to get all 4 possibilities, this is what we normally do. We go, P is true, true, false, false. Q is true, false, true, false. See, if you follow this convention, then see, you get all 4 possibilities right there. You know what I'm talking about? This is the conventional way to do it. You can do it any way you want, but this is the way most people do it. So what we're gonna do today is we're gonna start with this statement here. You see this symbol right there? You know what that means? If you look at your notes, what does that symbol mean?
And
It means and, or the conjunction. So the proper way to say this is the conjunction of P and Q. But we just simply say P and Q, because in mathematics there's a big difference between and or. Right? Now when is an and statement going to be true? When both of the components are true. So when both of these are true, that's when an and statement is going to be true. So look at this. Are both of them true?
yeah.
Yeah, so it's true. Are both of them true?
No.
No. Are both of them true?
No.
No. Are both of them true? No. So that's what the truth table looks like for the and statement, or conjunction. And then of course, if we have and, then of course we gotta have this. What do you think that symbol is?
Or.
That's or. Or we call that the disjunction of P and Q. Okay, now when is the or statement true? When at least one of these two components is true. So look at your two components. Is at least one of them true?
Yes.
Yup. Is at least one of them true?
Yes.
Yup. Is at least one of them true? Yup. Is at least one of them true?
No.
No, and there you go. Now, it's up to you how you want to remember it. Some people just memorize it. They go, oh, they'll just memorize this one, true, false, false, false. This one is true, 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 false. I don't think that's a good way to do it. You know why? Because sometimes it's not going to be like this because of something else. It's better to remember the and statement is true when both of the components are true. The or statement is true when at least one of them is true. That's the way you want to remember. Okay, now just based on these three things here, what you have to do tonight is you got to construct a truth table. Okay, let me just do one for you. Okay, let me think. Not P and Q not. Yeah. Okay, I need more space. Not P and Q not. Okay, construct the truth table for this statement here. So this is probably what you want to do. I'm just going to do. So this is like the training wheels. Okay, so what did I tell you? P is always going to be what? True, true, false, false. And Q is always going to be true, false, true, false. Okay? Now, some people are good at this, so they can simply look at it and they can write down the answer. If you cannot, then just go in steps. Like, if P is true, true, false, false, what do you think not P is going to be?
False, false.
It's going to be false, false, true, true, right? It's going to be the negation of all of these. Q, we know, is true, false, true, false. Now, you might say, well, it's written over there. Why do I have to write it again? You don't. Like I said, when it comes time for the quiz or test, I'm just going to look at your result. Basically, it's going to be 1 point for each one. Yeah? Now, I have these two columns like this. They are connected with and. So when is the and statement true?
Both.
When both of them are true. Are both of these true?
No.
No. Are both of these true? Are both of these true?
Yeah.
Are both of these true? No, so it's false. So this column here represents this. But now it gets negated. What's the negation of false, false, true, false?
True, true,
True,
false.
true, false, true. There you go. So this column here represents this statement. So we denote, we box it and we put an asterisk. Or do something to make sure you denote, like, or go, this is it. Right there. I think it's easier just to box it and put an asterisk. That's what I think. It's up to you. Now, I bet you some of you could just look at that and do this, right? Maybe not. Maybe you can't. It doesn't matter. All I'm going to do is, on the quiz, I'm just going to look at this. -1 for each one row. You get them all right? You can just do it by luck, right? Think about it. Just 50-50 chance every time.
Yeah. Yeah.
50-50 chance every time. What's the probability you get it all right? 1 out of 16. That's right. Go for it.
That's so smart.
Okay, let's do one more and we're done. Okay, now let's do one with 3. P, Q, and R. So how about P and not Q, or not P or R? Yeah, what the heck, let's put a not, negate that. Okay, construct the truth table for this statement here. Now notice that we have three different statements, P, Q, and R. So what does that mean? Like when it's P and Q, you got 4. So when you have P, Q, and R, what are you gonna have?
3 of those.
Yeah, you're gonna have 8 lines in your truth table. So if you need to, you make the training wheels like this. The training wheels are, here's P, Q, R. Okay, what's the pattern? So following the same pattern, what do you think? What do you think I'm gonna do for P here?
True.
True, 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 true. False, 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 false. What about for Q? True, true, false, false, true, true. See, if you do it systematically, then you don't have to worry about missing any. True, true, false, false. And what do you think about for R? True, false, true, false, true, false, true, false. Oh, I see the pattern now, Mr. Park. The one on the right always alternates by 1s. And then if you go 1 in, they alternate by 2. And you go 1 in, they alternate by 4. And so forth. So by the time we get to the test, you're going to have P, Q, R, S, and T, right?
Oh.
You're going to have, so if there's 5, how many lines in your truth table? You're going to have 32 lines in the truth table. So then what you do is, so P would be 16 truths and then 16 falses. Then the next one will be 8 true, 8 false, 8 true, 8 false. And then 4 true, 4 false, 4 true, 4 false.
This shortcut, or that's a shortcut.
It's the shortcut. Okay, let's see if we can do this mentally. Let's try not write anything down. Let's see if we can do it. So here's P. P is right here. True, 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 true. False, false, false. Not Q. Well, if Q is true, true, false, false, true, true, false, false, what is not Q going to be? False, false, true, true, false, false, true, true. And then I gotta AND them together. Connect them with AND. Okay, can we do it?
Yeah.
Okay, so what would it be?
True, true, false, 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 false.
Say that again? What's the first one?
True, true.
Okay, we can't do it then. Okay, so if you can't,
Not like false, false, true, true, false, false.
too late.
Not like-
So if you can't do it mentally, see, when I say mentally, I mean like in your head, not like crazily. So,
not like-
true, true. Hey, don't be afraid to write it again. Don't be afraid. And then what would not Q be if Q is true, true, false?
False, false.
False, false, true, true, false, false, true, true. See, it would be good to do this on like folder paper because then you have all the lines, yeah? Now, and, the and statement is true when both of them are true. Are both of them true?
Oh, no.
No. Are both, what am I saying? Are both of them true?
No.
Are both of them true? What am I doing for?
Yeah, wait.
Are both of them true? And then no, 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 no. Okay, so this column represents that. Now we gotta do this. Now, what is not P? If this is P, what is not P? False, 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 true, 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 true. So let's write that. False, 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 true, 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 true. Oh, the lines are not even lining up. We need lines. And then what is R? True, false, true, false, true, false, true, false. Okay, now I gotta connect these two with OR. When is the OR statement true?
One of them is
When
one.
at least one of them is true. Is at least one of them true?
Yes.
Yes.
Is at least one of them true?
No.
No.
Is at least one of them true?
No.
Is at least one of them true?
Yes.
Are you my mother? Are you my mother?
The
Are you my mother? Are you my mother?
Yeah.
Yeah, there you go.
Wait,
So
the third
this column represents that. But then now I gotta connect these two with OR. When is the OR statement true? When at least one of them is true.
You guys are like muttering back here. What's up?
The third one is true.
Where? Yeah, that's what I said. Are you my mother? No, that's what happens when you get older. You start thinking ahead and then everything goes to hell right there.
No.
Okay, so look at these two now. Is at least one of them true?
C.
Is at least one of them true? Are you my mother?
Yes.
Are you my mother?
No.
Are you my mother? Are you my mother? Are you my mother? Are you my mother? Okay, so this represents this, but then it gets negated. So what is the negation of all of these going to be? False, true, false, 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 false. Oh, so this column represents, maybe we better double box it because it kind of looks like those. Double box with an asterisk. Yeah, I like that better. Double box with an asterisk. It's pretty mechanical, right? This is not difficult concept. You just memorize certain forms, that's all you gotta do, easy.
How do you do the or in between again? In between the two?
Well, see, this is just like regular mathematics, you gotta do what's in the parentheses first, right? So you gotta do this first, and then you gotta do that first, and then you gotta connect these two with or, right?
So like there's.
So that's why you wanna make one thing for this, that's this column here.
Mhm.
This thing here is this column here, but then now you gotta connect these two with or. And that's gonna be this, and then you gotta negate all of that. So again, you just follow the same rules of mathematics, whatever's in the parentheses has to be done first. Oh, Mr. Park, if you just had one more false here, it would be all false. But it's not. But what if it were? What if that was a false? What do you call a statement that comes out false every single time, no matter what?
Not good.
It's in the, I'll give you a hint, it's in the notes. It runs in contradiction. It's a contradiction. So if you come across a statement in tonight's homework that comes out false every time, we call that a contradiction. What do we call a statement that comes out true every single time?
Non-proof.
It's called a tautology.
Okay, yeah.
It's in the notes. Believe me, everything you need to know is in the notes. You just gotta look there. Just like last year's class, they're so hard-headed. If they would just look in the notes, they would know things. But no, I'm going to be big man on campus. I'm not going to look at the notes. I know everything already.
Yeah.
All it takes is a couple of failures, and then they realize you should be looking at the notes. Okay, tonight's homework, easy, fun. I would guess with your mathematical ability, you should be able to do this in like 10 or 15 minutes. Now, when you do your homework, you do not need to rewrite the problem because the problem is written already. You know what I mean? Why write it again? You know what I'm talking about? So here, this is all you gotta do. So like problem number 1, it says for all integers k plus 1 is also an integer. So write the negation of that. What's the negation of a universal statement? So there exists box, what's the box? An integer k. K is an element of the integers such that, then you gotta negate the triangle part, what? K plus 1 is not an element of the integers. Boom! See, right? You can do that in like 5 seconds. Unless you want to write it out in words, then it might take you 10 seconds. Like I said, I don't care whether you write it out in words or you write it out in letters and symbols. As long as it's correct, that's the main thing.
Then that's false, right?
No, I'm not going to tell you. Anyway, got that. It's yourself a bottom. Oh my gosh, we went to the end. We're supposed to finish it. Good thing we had extended there. We're in trouble. Okay, we'll see you tomorrow. Well, I know why it took so long. We had to do remedial math, that's why.